Okay, some more module 9. We are going to continue with quantum mechanics. So let me share my screen. All right, so we were talking at the end of the last lecture about the fact that I can't really tell where an electron is exactly in an atom. All I can really tell is where there will be a high probability of finding it. And we really want to understand this because many of the properties of atoms are related to the energies of electrons. Bonding occurs with electrons between two different atoms. So molecules are built on bonds that form between atoms because of their electrons. So where are they? Where exactly are those electrons in an atom? Schrodinger did a huge amount of high-level math and came up with something called the Schrodinger's equation, which allows us to calculate the probability of finding an electron with a particular amount of energy at a particular location. Now, we're not going to do this math. This math is something that you would see in senior level chemistry classes that were calculus based, or even graduate school, which would be calculus based as well. All I can tell you is that solutions to Schrodinger's equation produce something called a wave function, which is this, I think that's a psi. Now, if I do a plot of distance versus y squared, or psi squared, what I get is a representation of an orbital. Now, this is not the orbit from the Bohrs where I'm sort of circulating around the nucleus like the planets are around the sun. This orbital is actually a probability distribution map, and it defines a region where the electron is likely to be found. So this is sort of the pathway. I have a wave equation, I solve it, I have a wave function, and then I can calculate the probability of finding that electron in a region of space, which is going to be my orbital. So wave functions are actually characterized by 3 different parameters, which are called quantum numbers. And right now, we're going to focus just on 3. We're going to look at N and L and M sub L. And these are quantum numbers which result from the wave equation, which is the solution of Schrodinger's equation. So let's go into what these quantum numbers are. The first one is called the principal quantum number, and that's M. This actually describes the size and the energy level of the orbital. This has also been called a shell, and it's always a positive integer. So N is going to be 1, 2, 3, 4, etc., etc., etc. As the value of N increases, the energy of that orbital increases, and that average distance of the electron from the nucleus also increases. These can also be looked at sort of as Bohr's N values, where I can have N equals 1, and then in my next shell I have N equals 2. And as I go farther and farther and farther away from the nucleus, my N value increases. So in hydrogen, my energy levels look something like this. I have N equals 1, and then notice I have a very large gap between n equals 1 and n equals 2. There's a lot of energy that separates the first energy level from the second. And then there's another amount of energy that separates the second from the third, but that's a much smaller value of delta E. And then as I continue up, these energy shells become these delta values, right? The energy difference between each successive shell gets lower and lower and lower. And that has some significance when we talk about how electrons are populating the atoms. So my largest delta E is between n equals 1 and n equals 2. The second largest will be between n equals 2 and n equals 3. And then they get, those successive delta E's get lower and lower and lower. So again, this is going to compare to my Bohr's energy level. And remember, my energies are defined as being negative. When my E equals 0, or when my N equals infinity, that would be called ionization. And that would be when my electron actually leaves the atom. So I can calculate ionization energies using that Rydberg equation if I set N final as N equals infinity. Again, these values are positive, and the larger value of N, the larger the orbital. So as I mentioned, as N gets larger, the amount of energy between the orbitals gets smaller and smaller. The next quantum number is L, and this is called the angular momentum quantum number. This is what actually defines my three-dimensional shape of that orbital. This is also called a subshell. There are n different shapes for orbitals. If n equals to 1, then I only have one choice for L, which is 0. So it's n minus 1. If n equals 2, then I can have either an L value of 0 or 1. If n equals 3, then my L value can be 0, 1, or 2. Now, if you've taken chemistry before, especially in high school or maybe an intro class, what you're going to notice is these letter designations for the shape of the orbital. S orbitals are, the reason they're S is because they're referred to as sharp. Then I have principal, I have diffuse, and I have fundamental. But we're going to see that the shape of this later, this is going to be spherical. This is going to look like a dumbbell. This is going to look like a clover leaf. And this just looks like a mess of lobes. But the important thing is, S is always the first orbital in a subshell, and S is always L equals 0. If I know I have S, P, D, F, each one of those types of orbitals increases in energy, and my L value also increases. I have 4 types of orbitals that we're going to really become familiar with, the S, the P, the D, and the F. And I have 4 values of L that we're really going to become familiar with. Any S orbital has an L value of 0. Any P orbital has an L value of 1. Any D orbital has an L value of 2. And any F orbital has an L value as 3. So this perpendicular, or this L, is called a particular letter, or each value of L is called by a particular letter, which designates the shape. So remember, S is going to be spherical, P is going to look like a dumbbell. So if I think about a dumbbell, right, think about 2 balloons tied together at the knots. D orbitals, think about 4 balloons tied together at the knots, or else it's sort of like a clover leaf. And then F orbitals actually look like 8 balloons sort of tied together at the knots. And that's a much more complicated system. So obviously the S is going to be the lower energy, less complex system. As I increase in energy level, I increase the number or the type of subshell that's available. So you want to think about that as well. I also have something called a magnetic quantum number. And this is the spatial orientation of the orbital. This is the direction in space the orbital is aligned relative to the other orbitals. So we're going to look at the XYZ plane. If I look at sort of the coordinate plane, I'm going to define all my orbitals and my spatial orbital or my spatial orientation of orbitals. Do they lie along the x-axis? Do they lie along the y-axis? Do they lie along the z-axis? Are they in the xy plane? Are they in the yz plane? We're going to use the coordinate system in order to designate the direction in space that the orbital is aligned relative to all the other orbitals. Now, there are 2 L+1 values of m sub L. I don't really use these formulas to calculate them. I just want to understand what's happening. So they go basically from -1 to +1. And if I have an L equals 0, so this is going to be an s orbital, I only have one choice, and that's always going to be m sub L equals 0. So if m sub L is 0, -0 to +0 is 0. If m sub L equals 1, then I have 3 choices. I can have m sub L going from -1 to 0 to +1. If m sub L equals 2, right, this would be the d orbitals. I have 5 d orbitals, and I'm drawing these orbitals like boxes. The center is always 0. Then I just count up, +1, +2, -1, -2. So when I look at it in that context, my possible m sub L values for any d orbital is between -2 and +2. So there's 5 different choices. There's 5 different possibilities for that m sub L. When I go into L equals 3, then m sub L is going to be -3, -2, 0, 1, 2, or 3. I have 7 choices because there are 7 f orbitals. 1, 2, 3, 4, 5, 6, 7. The central one is always 0. Then I count up. And then I count down. And I get all of those choices. So an electron in subshell L equals 3 can be oriented in 5 different ways. It can have these m sub L as 5 different numbers, which represents those 5 different spatial orientations. So this chart shows you the values of n, L, and m sub L. And notice these are my energy levels. My energy levels will go from 1 to 2 to 3 to 4, right? And higher. Those are the energy shells. The L is the type of orbital, S, P, D, and F, and the m sub L is the orientation. Now here, I have this orbital notation, which you're going to see a lot of. If I'm in n equals 1, the first energy level, and remember, my L equals 0 is S, L equals 1 is P, L equals 2 is D, and L equals 3 is F. My orbital notation is going to lead with a principal quantum number, and then based on the L, I'm going to write the letter. In my first shell, the only thing I have is an S subshell. So that's going to be a 1s orbital in the first subshell. When I go, or in the first shell, when I go to shell 2, energy level 2, I have two possibilities. I could have 0 and 1. So I actually have S and P. That's in the second shell. So I have 2 s orbitals and 2 p orbitals. There are 3 types of p orbitals available. So I have these 3 different values of m sub l in that. As I go to energy level 3, now I have 3 different choices, right? I have my s, my p, and my d type orbitals. So notice the first time I encounter a d orbital is in energy level 3. And again, I have the various m sub l because there's 1s, there's 3p, and there's 5d orbitals. So I have 1 value here, 3 value here, and 5 m sub l's for the d. This is the number of orbitals. In any s subshell, I only have 1 orbital. In any p subshell, I have 3. And in any d subshell, I have 5. When I get to energy level 4, now I have 4 different types of orbitals available. I have the S, the P, the D, and the F. Remember, the S subshell only has 1, the P subshell has 3, the D subshell has 5, and the F subshell has 7 orbitals available to it. So I have these designations. The principal energy or the principal quantum number always leads, and then I have that orbital notation where it's either S, P, D, or F. And that notation depends on the value of L. So notice as I go from shell 1 to shell 2 to shell 3 to shell 4, the number of orbitals are vastly increasing. So I have a lot of orbitals in these various subshells. Think about that. I have, 118 atoms that I have to account for. That 118th atom has 118 electrons. So all of these electrons, when they populate the orbitals of these atoms, as I get more and more and more complicated, as I add more and more and more electrons, I need places for them to go. So the complexity of the orbitals, the energy of the orbitals keeps getting higher and higher. We max out at the F level, the F subshell level in all of the elements that are known right now. Theoretically, this designation can go on and on and on if we ever discover any more elements. So each set of N, L, and sub L describes one orbital. It's like an address, right? These quantum numbers give me the address of an electron. If I have orbitals with the same value of N, they're all going to be in the same principal energy level. If I have the same values of N and L, they're going to be in the same sublevel. Remember, this can also be a shell or a subshell. That terminology is basically interchangeable. So, as I go from n equal 1, I'm going to use these boxes to represent orbitals. As I go from n equals 1, I have one subshell, which is S. My L equals 0. My M sub L equals 0. I can only hold 2 electrons because each orbital can only hold 2 electrons. So as I go up to energy level 2, I've got 2 sublevels. I have the L equals 0, or the 2s sublevel. I only have 1 orbital. Any s sublevel only has 1 orbital. and my M sub L has to be 0. When I go up in that second subshell, I'm looking at, now I have L equal 1 orbitals available. That's the 2p sublevel. I have 3p orbitals. And again, now I have 3 different possibilities of the orbitals, of the M sub L's. So as my energy level increases, the number of orbitals in my levels increases, and the number of subshells increase as I go up. Notice in n equal 1, I have no p, no d, and no f. I only have s orbitals. Here, I get my first p. So I have s and p, but I have no d or f. In the third shell, I have s, p, and d orbitals, but I have no f orbitals. F orbitals will come in the next shell, which is my n equals 4. So I'm starting to build the framework for how the orbitals are oriented around the nucleus of the atom. Because this orbital framework is where my electrons are going to be located as I start building different elements. Remember, hydrogen only has 1 proton, 1 electron. Where is that electron going to go? It's going to start here. As I get more complex, as I increase the complexity of the atom, I add more protons, I add more electrons, those electrons are going to have to go in more orbitals. So in helium, I'm going to have 2 electrons, and so on and so on. So as each element builds upon what came before, I have to put these electrons in these different subshells. And thus in those different orbitals. Had a little tickle there, had to take a glass of water. Okay. So in general, the number of sublevels I have within a level is equal to the principal quantum number. So in n equals 1, I have 1 sublevel. In n equals 2, I have 2 sublevels. That sort of stops after n equals 4. So you have to sort of, then I start getting into theoretical sublevels. So really, I'm focusing on the S, P, D, and F sublevels, which when I get into energy levels 5 and 6 and 7, I'm still dealing with these sublevels. The rest of them are still theoretical. The number of orbitals is always going to be, for S, I have 1. For P, I have 3. For D, I have 5. And for F, I have 7. You can calculate it. I don't really pay any attention to that. I just think about where I am in my periodic table, which is going to be a really useful reference for building these atoms. And then I'm looking at these fundamental ideas where any S subshell only has 1 orbital, any P sublevel has 3, any D sublevel has 5 orbitals available, and then the F has 7. And that's really all I need, even if I do have theoretically more as we go on in the periodic table. So we're just going to work with sort of keeping it simple here. The number of orbitals in a level is n squared. That's a sum. The number of orbitals in a level is the sum of all the orbitals in the subshell. So if you notice back in this slide, here I only have 1 orbital because I have 1 sublevel which only has 1 orbital. Here I have a sublevel that has 1 orbital and a sublevel that has 3 orbitals. So I add those to get 4. And so on and so forth as I go down. Okay, Now, hydrogen is well studied. Hydrogen is what we based a lot of our quantum mechanics on because it's simple, right? Keep it simple, stupid. Right? Isn't that kind of a mantra? Hydrogen is one proton, one electron. So that one electron is probably the most studied electron in the history of science. In fact, it is the most studied electron, right? And what we know in hydrogen is that when I have a subshell, for example, in the second level, the S subshell and the P subshell are equal energy. In the third subshell, or in the third energy level, all of the subshells are of equal energy. And that's the same thing in the fourth subshell. As I add electrons, the picture becomes much more complex. So this setup only applies to hydrogen, which is one element out of 118 that are listed on the periodic table. So this is a much oversimplified view of what we need to know for the rest of the elements. Although I would like you to know that hydrogen has in every sublevel, or every shell, all the sublevels are equal energy or degenerate. As I go into these more complicated multi-electron systems, the picture gets really, really complex. So, for example, my 2p orbitals are higher in energy than my 2s orbital. My 3d orbitals are higher in energy than the 3p orbitals, which are higher in energy than the 3s. So generally, S is lower in energy than P, which is lower in energy than D, which is lower in energy in F. But notice here, if I draw a line out this way, my 4s is actually lower in energy than the 3d orbitals. There's some crossover of energies between one shell and another. So in some atoms, my 3d orbital has a higher energy than a 4s orbital. I fill and populate orbitals based on energy. So the order of filling of my orbitals gets a little bit complex because I do have some crossover. So if I look at the energy, 1s is the lowest, then 2s, then 2p, then 3s, then 3p, then 4s should fill before 3d. The next to fill would be in the 4p, and then the 4d, right? So you're going to see that I have some crossover. And this happens with the s orbitals, which is why I'm going to teach you how to use the periodic table in order to do your electron configurations, in order to figure out how these different electrons populate these orbitals, because it's the easiest and most efficient way to look at how electrons make these individual elements and how they populate the orbitals around the nucleus. So here's an example. Identify the possible values for each of the three quantum numbers for a 4p orbital. So my orbital is 4p, and I have n, l, and m sub l values that I want to designate. Well, the n is easy. It's that number that designates the shell. So n equals 4. Well, my L value is going to be the value for P. Remember, L equals 0 is S, L equals 1 is P. So that's going to be 1. My M subshell, remember my P subshell has 3 orbitals. The middle is 0, then I have +1 and -1. Those are my sub L values. So in my 4p orbital, I could have, notice this word, possible. My M sub L can be -1 or 0 or +1, depending on the orientation of that orbital. So you have to sort of consider each of these values one by one. Now, how does this all explain atomic spectroscopy? Each wavelength in the spectrum of an atom, right? The wavelength in the spectrum of an atom corresponds to an energy transition between orbitals. When that electron is excited, it's going to transition from a lower energy to, it's going to go from lower to higher. It's absorbing energy. My higher level orbitals are going to be higher in energy. When that electron relaxes, it's going to transition from that higher energy level to an orbital in a lower energy level. When the electron relaxes, that energy has to go somewhere, right? I'm going from a higher energy system to a lower energy system. What happens to the energy? Well, it emits this photon of light corresponding to that amount of energy. So the energy of that photon of light equals the energy difference between the orbitals that that electron is transitioning from. So to transition to a higher, if I want to go from low to high, I have to gain the correct amount of energy that is exactly, has exactly the amount that is the difference in those energy levels. Electrons in high energy states are unstable. They tend to lose energy. Everything wants to seek an energy minimum. So if I add energy, I can promote that electron, but it doesn't want to stay there. So at some point it's going to relax, transition to that lower energy state, and then emit that photon. So each line in my emission spectrum corresponds to the difference in energy between two energy states. So for example, if I have an electron in n equals 1, it might absorb this energy and transition to n equals 3. Now remember, I can use the Bohr-Rydberg equation to figure out that amount of energy. Remember, my delta E is equal to that constant, and then I have 1 over n final squared minus 1 over n initial squared. So I can go ahead and figure out what exactly that the difference in energy is between n equals 1 and n equals 3. Now let's say this relaxes down to, from the n equals 3 to the n equal 2 state. What it gives off is this photon, and it's this squiggly line because it's trying to sort of indicate a wave. So my light is emitted, and the wavelength of the light that is emitted corresponds. Remember, E equals hc over lambda. So this energy difference between n equals 3 and n equals 2 is going to be able to be calculated if I know the wavelength of light. I could also use this equation if I know the energy levels. All of these things are interconnected and they're intertwined. So when you think about doing problems, you have to think about all of the electrons that are going to, all of these equations that we're going to use and how they sort of all go together. Okay, this gets a little tricky, and we don't really, I mean, this is sort of out there a little bit. We're just going to talk about it a little bit so you guys, I can say that I did it. Remember, this psi squared is the probability density, the probability of finding an electron at a particular point in space. So for an s orbital, I have a maximum at the nucleus. Remember, if I have my positively charged nucleus, those electrons want to be close to the positive charge. Those are attractive. So the highest probability of finding an electron in an s orbital is at the nucleus. The probability of finding that electron in that s orbital decreases as I move away from the nucleus. This can be represented by something called a radial distribution function. This represents the total probability at a certain distance from the nucleus. The maximum is at the most probable radius or distance from the nucleus. There are things called nodes where the functions, these are nodes in the functions where the probability drops to 0. So there is absolutely 0 chance of finding electrons when I have a node. So let's look at an s orbital. The probability density function represents the total probability of finding an electron at a particular point in space. So again, remember, I have my dots. The larger the blue density, right? I'm looking at the density of dots. The darker the blue, the higher the probability. So these density of dots are proportional to the probability density. However, if I look at this curve, this is going to say, here's my distance from the nucleus, right? If this is 0, as I go away, here's my highest probability of finding the electron in this s orbital. And you can see, hopefully, that you get bluer as I go in towards the origin, which would be the nucleus. And then as I go away from the nucleus, my probability is dropping substantially. So here I have very little chance of finding that electron. I've sort of exceeded the boundaries of that orbital space theoretically. Now I can turn that into this radial distribution function, which actually looks at that total radial probability as a function of distance. Now notice this radial distribution function represents this total probability of finding an electron within a thin spherical shell. So I'm in my s orbital, I'm in the 1s orbital, and I want to look at the distance. So at 52.9 picometers, that is the most likely distance away from the nucleus that those electrons are going to be found. So notice this probability decreases with increasing distance from the nucleus. But the volume of the spherical shell increases. So you have sort of two competing factors. I have this increasing distance which lowers the probability, but I'm increasing the volume which increases the probability in a way. So when I take those two competing factors and I get this function, I can indicate what I see is that the most probable distance of an electron in a 1s orbital of hydrogen is 52.9 picometers. So what does this mean? It means that the probability distribution for a 1s orbital has a maximum at a distance of 53 picometers. This is the most likely radial distance of the electron from the nucleus. As the electron gets closer to the nucleus, the probability would increase, but the volume of the sphere would decrease because I'm sort of squeezing it down, right? I'm looking at spheres, so the closer to the nucleus is, the smaller the sphere, so that volume would decrease. So the probability of finding that electron in such a small volume is very low. Again, these are two competing trends. As the electron gets farther away, the volume increases, but the electron probability function decreases, so the electron density decreases. So I have this electron distribution being represented by two competing factors. I have increasing volume and decreasing probability of finding the electron in a given layer. So when I look at the s orbital, I'm looking at it as if it's a sphere, and I'm sort of giving it a boundary. This boundary is basically a 90% sort of confidence interval. At this boundary of this orbital, I can actually sort of safely say that 90% of the time the electron is going to be found within this space. There are outside factors, right? It's not 100% probability. So sometimes the electron can be found outside of this space, but we're kind of looking at what's most probable. So each principal energy level has one s orbital. This is the lowest energy orbital in any given energy level. It's going to be spherical, and the number of nodes is n equals 1. So when I'm in shell number 1, I have 1 minus 1, I have 0 nodes. So there is no place in this volume that the electron cannot be found, because when I have a node, I have 0 probability. Or actually, I don't want to write that there. I want to say when I have a node, I have 0 probability. There are no nodes in the 1s orbital. If I go to larger orbitals, here I have the 2s orbital. I have a node where I have that 0 electron probability. So remember, 2 minus 1 gives me 1 node, which is indicated by that white space. So the electron can be found here or out here. It will not be found in this white space. That has a node. For 3s orbitals, I have 3 minus 1. I have 2 nodes. So again, I have this white space and I have this white space where I have 0 electron probability, which is my node. So you can see the nodes in these depictions, and I'm showing this with different colors of different regions. Those different colors actually correspond to different algebraic signs of the wave function. And basically, it's like having different phases of a wave. So when I get to compare a 2s and a 3s orbital, note I have that node, right, which is corresponding to when I have 0 probability. The most likely place to find the electron is still close to the nucleus, but there's another area of high probability, which is out beyond the node. I have a small chance of finding it close to the nucleus. I have a larger chance of finding it a little bit farther away from the nucleus in my second orbital. Because remember, my 1s orbital is there also. So that orbital space has already got electrons. As I go to the 2s orbital, I am making more space around the atom so I can populate it with other electrons. Here for the 3s, again, I have 2 nodes, and I have sort of a small probability there, a larger probability. Here's my largest probability at a distance farther away from the nucleus beyond that second node. And this is going to have, is going to be the distance from the nucleus that has the most probable chance of finding the electron there. So again, you just have to know this sort of in a sort of overview manner, maybe some sort of conceptual type question. Then I'm going to look at p orbitals. When I have a principal energy state above n equals 1, right, it has to be 2 and higher. And then I can get that 3 subshell, which has 3 individual orders, 3 values of m sub l. Now, each of these orbitals points along a different axis. So the p sub x is pointing along the x-axis, the p sub y points along the y-axis, the p sub z points along the z-axis. This is the second lowest energy orbital. Remember, s is lower in energy than p, which is lower in energy than d, which is lower in energy than f. These have 2 lobes, and I have 1 node at the nucleus. So I have n nodes. I have the same number of nodes as I have energy levels. So if I look at these, here is my p sub x, and notice it's along this x-axis. Here's my p sub y, it's along the y-axis. Here's my p sub z, it's along the z-axis. Notice I do have these node values where I have 0 probability. So here's the most likely distance that that electron is going to be found in a 2p orbital, which is going to be this radial distribution function. Now notice that this is the composite view. These p orbitals are there all at the same time. So they sort of make this overlay where I have the x and the y and the z orbitals sort of represented by these individual p orbitals. So just remember, all these orbitals are sort of building on top of each other, starting with the 1s. When I look at d orbitals, this is where L equals 2. Remember, I have 5 of those d orbitals, so I have 5 m sub l values. 4 of the 5 orbitals are aligned in a different plane, and then I have something aligned with the z-axis. These are designations, just like the px, the py, and the pz. These are the 3rd lowest energy orbitals I have. They're higher than s, higher than p, but they're lower than f. They have 4 lobe, but I have this one special one, which I like to call a dumbbell with a donut. This is 2 lobe with a toroid. Higher principal energy levels also have spherical nodes. So this is what they look like. Kind of like a clover leaf. Notice this orbital is found in the YZ plane. The orbital isn't aligned directly with the axis, but it's sort of pointing out in this direction, but it is in the plane defined by the Y and the Z axes. Here I have this direction, it's the plane that's found along the X and the Y axis, but then here I have this XZ. This is where I have x squared minus y squared, which is another orientation. It's a little bit different than this one. They're offset. If you look at these two, they're sort of offset. And then here's my dumbbell with a donut, which is my z squared orbital. And notice I literally think it looks like a dumbbell with a donut. But there's 5 of these orbitals. They're complicated. They have all these lobes, and they are all in different orientations. Those electrons don't want to be on top of each other, right? Because they're negatively charged. I can't put those electrons totally on top of each other when I want to build my atoms. So these wave functions are giving these spaces where they're in the same energy level, but they're a little bit different oriented, different M sub L's, so that my electrons have room to be as farther away from each other than right on top of each other. When I get to the F orbitals, right, I have 7, this should be F orbitals, and I can have 7 different values of M sub L. This is going to be that highest energy. They're mainly 8-lobed. Some have a toroid, and I do have planar nodes and spherical nodes. But this is what they look like. These guys, again, here I have a toroid, here I have a toroid, but notice now I have sort of 2 spaces. It's not just one donut, but there's 2 donuts. And these, you're not going to be able to remember these sorts of designations. I don't remember them. What you should be able to do is recognize if you see any of these shapes that they're F orbitals. Remember, they have these complicated 8 balloons tied together, or these toroids where there's multiple toroids within the axis. So you should know the shapes of all of those different orbitals. And if I give you a picture of one on a test, you should be able to tell me if I'm giving you a picture of an S, a P, a D, or an F orbital. One more thing is phases. Remember, these orbitals are determined from mathematical wave functions. These functions can have positive or negative values, as well as nodes where the wave function is equal to 0. That's when I have 0 probability of finding an electron. The sign of the wave function is called a phase. Now, when orbitals interact, their wave functions may be in the same sign, or may have the same sign, which means they are in phase, or they may be out of phase, which means they have opposite signs. This is important in bonding. I have to have an in-phase interaction to form a bond. If they're out of phase, I'm not going to form a bond. And this is going to be examined in a later chapter. So this is what it would look like. This only has 0 nodes, so it only has a positive solution. Here, this would be positive and this would be negative. The blue color is sort of arbitrary. There are books where the red is negative and the blue is positive. Just note that if I have opposite colors, right, this is positive, this is negative, if this is 0. So in our book, we have positive values of the solution of the wave function being blue, and then the other phase is going to be, the other sign is going to be indicated by red. Each p orbital, right, has these 2 lobes of high electron probability. This is that nodal plane that passes through the nucleus. Again, remember, these different colors of those lobes just represent different algebraic signs. And that is analogous to different phases of a wave. Again, these are also color depictions. I have positive values in the blue, negative values in the red, and you can see that this is a plot based on the solution of those Schrodinger equations, which gives me the most likely area to find an electron. So why are atoms spherical? Well, it's because all of these electrons sort of build on, all of these orbitals build on each other. Everything starts at the nucleus, which is 0, 0, 0 on my coordinate plane. And then I just keep building and building and building and getting larger and larger and larger And everything is sort of encapsulated in a larger size S, which is spherical. And we'll talk about that more as we go further. So this is the end of Module 9. And next time I meet with you, I am going to talk to you about Module 10, which is actually building electron configurations and assigning which orbitals these electrons in the atom are actually populating. So see you in a bit.